We are talking about rational functions. So we talked about asymptotes on Friday, but we never really talked about what a rational function is. Let's just do it here. Okay. So here are examples. Here's 6 rational functions up there. I think did we analyze some of these at the end of class last time? Okay, so let's define what is a rational function. So what do you notice about the form of all these functions? What's that? Ratios, right. The ratios of what? Ratios of what kind of functions? Polynomial is the last thing we got done with. So if you take one polynomial, divide it by another polynomial, you get what's called a rational function. So we'll call it n of x for numerator, d of x for denominator. So nx and dx are both polynomials. So much of the stuff, all of the stuff that we learned about polynomials is totally valid here and important for these. Okay? So the first thing we're going to talk about is we have, everyone got that? I'm going to erase this and use this space again. So again, rational function, take one polynomial, divide it by another, you get a new function, which we call a rational function. So I'll just write it up here. So let's start with roots. Roots are, what's the definition of a root? A root is? Okay. They said x-intercepts or values of x that do what? Make the function equal to 0. So what's that? Y, right? Y equals 0. So values of x that make it 0. So if we have a rational function, how are we going to get a fraction to equal 0? How do we get a fraction to equal 0? 0 divided by anything is 0, right? So we specifically, the roots of a rational function are the roots of the numerator. Common mistake. Students find both the roots of n and d and say those are all roots of the rational function. Not true. We want the roots are specifically values of x that make it 0. So we need that numerator to be 0. What's that? We did. And were those the roots of the equation? Those x-intercepts? Yeah, remember? We do find the roots of the denominator, but they are not the roots of the rational function. That's right. What about y-intercept? The denominator is equal to 0. Does that give us our y-intercept? What's true about a y-intercept? There's only one way to make x 0. So set x equal to 0, right? Okay, or n of 0 over d of 0. That gives the y-intercept. You plug 0 in for x, and it gives you the y value where x is 0. That's the y-intercept. Vertical asymptotes. Yeah, this is the roots of denominator. values of x such that st is such that st such that values of x that make the denominator 0. So things get haywire when you try to divide by 0. If you get close to that, we saw in with some examples last time why the function either gets very, very large positive close to a 0 in the denominator or very, very large negative close to a 0 in the denominator. And you just plain can't put a 0 in the denominator, right? So that's why there's a break in the graph. There's a break. And it doesn't exist. So, again, the common mistake is that students think that all of the roots of both n and d are the roots of our rational function. But that's not true because the roots of d give us undefined values for y. Okay? And that's not a root. Okay? That's undefined. That's where the vertical asymptotes are. Okay, the last thing we have to look at is end behavior. We didn't do that last time, but once we've got this, we can put everything together and sketch these graphs. So the end behavior works similar to how we did before. How did we find the end behavior of polynomial functions? Okay, we looked at the leading term. Well, now we got two. We got two polynomials, and we're going to look at the leading term of n, and we're going to also look at the leading term of d. And then we're going to simplify that. So because those two values, the leading terms of each of those, as x gets very, very, very large positive or very, very large negative, will govern their respective polynomials. All the rest of the polynomial will be like 0. So then we will simplify the ratio of the leading terms. And that will be what we're going to call the effective end behavior is the ratio of the leading terms. Effective end behavior. I'm out of room, but it would be the ratio of the leading terms of n and d. Will be like our effective leading, it's not effective end behavior, it's like effective leading term, effective leading term. That's what I meant to say. The effective leading term is what you get when you divide the two leading terms. You get a new term, and that's like the effective leading term for the whole ratio. And we'll analyze end behavior the same way. We'll take that effective leading term and we'll say as x gets very, very big positive, what will that effective leading term do? That's what the rational function will do. And as x gets very, very large negative, we'll look at that effective leading term and analyze it. And that's essentially what the rational function will do. So let's take a couple examples. What would the effective leading term, ELT, what's the ELT of x over 2x minus 8? What's the effective leading term of x over 2x minus 8? X over 2x, which equals, and then you simplify it. So as x, so equals 1/2. So as x gets very, very large positive, what will the function get close to? Will it go to infinity? Nope. We'll go to infinity. It'll get close to 1/2. Y equals 1/2. And as x gets very, very large negative, it'll get close to 1/2. So this is what we'll call a horizontal asymptote. So a horizontal asymptote of y equals 1/2. As x gets very, very large positive, the function, the graph, will get very, very close to y equals 1/2. Because that's our effective leading term, 1/2. As x gets very, very large negative, likewise, the graph will get very, very close to positive 1/2. Okay, what's the effective leading term for mx here? So what's our effective leading term there for mx? How would you find it? x over x squared. Effective leading term is x over x squared, which is, simplify it. One over x. As x gets very, very large positive, what would mx do? It's going to be like 1 over x. So what if x gets very, very large positive, what does 1 over x do? Goes to 0. And as x goes to negative infinity, also close to 0. You take 1 over a very, very large number, it's like you keep dividing. It's like you're dividing something into more and more pieces, and you're asking how big is each piece, right? You keep dividing something like a pizza. Keep dividing it in more and more and more and more pieces. How much pizza is your piece going to be if you keep doing that? Eventually none, right? So eventually, if you divide a pizza in an infinite number of pieces, each piece will really have nothing, right? Okay, let's look at another one. How about n? So find the effective leading term. Effective leading term and n behavior. So find the effective leading term and analyze the n behavior for that. Go. So what is the effective leading term? For part E, which is n of x. What's the effective leading term? X cubed. X cubed, right? So it's just like we had a polynomial and our leading term was x cubed. As x gets very large positive, y does what? Y becomes positive infinity. As x gets very, very large negative, x cubed goes to negative infinity. So your n behavior is like this. Up to positive infinity when x is positive, down to negative infinity when y is negative. Okay, so the new situation here is when we have a constant like this, or the 1 over. When you have a constant, see, this has nothing to do with x. So as x gets very, very, very large, y just gets closer and closer to that number. That's a horizontal asymptote. Same with as x gets very, very large negative, y gets closer and closer to 1/2. Okay, so what I want you to do is on page 241, you've got 4 to analyze there. I'm going to kind of change the questions though. So don't start yet, just listen. So for number 1, you're finding the zeros or roots of the function. Thumbs up, okay? Do number 1. Then number 2, find the vertical intercept. Thumbs up. For number 3, I want you to find the vertical asymptotes. Find the vertical asymptotes in number 3 instead of the domain. Which is actually, those are very closely related, right? The vertical asymptotes are the points that we kick out of the domain. They're gone. Okay? Number 4, find the effective leading term and n behavior. Instead of, I don't know what they're referring to there. So using what you just learned about End behavior, find the effective leading term, and end behavior. That's number 4. So you're doing all 4 things for those 4 functions, and then we'll see which ones you want to talk about. And if you have time, you can graph them. So they give you 4 graphs on the next page. Don't use your calculator. The whole point is, can we analyze the equation and come up with a graph? So don't use your graphing calculator. Is the task clear? So 1 is good. Do number 1. 2 is good. Do number 2. Number 3, do the vertical asymptotes for number 3. And for number 4, do the effective leading term and end behavior. And then we'll regroup.
Yeah. Vertical intercepts. So like y intercept is the bottom of the intercepts. Right? Y. It's imaginary. How do you find 0? Is it?
Oh, there it is.
No.
It's basically the 1%. So when you put x to 0, move the x to 0. Isn't the vertical intercept basically y intercept? So then you just plug over 0. So then it would be negative 3 over 2. It's a fraction.
It's a ratio.
What fraction?
You go right, that's right.
Wouldn't the y-intercept for number 2 be 0 or 1?
For this? 0 over negative 1 times negative 3?
0 over 3.
0
Okay,
divided by negative 1 divided by negative 3.
yeah, I didn't
Oh, thank you.
just flip your pen. I was going to. It was faster than I do.
Do you want to do some graphs? So check your work. Here's all this. So ask questions as you're checking. So can you tell me a value of x that will make that 0? What did you think it was? 1 squared plus 1 is 2, not 0. How about negative 1? Still 2, right? So there's no value of x you can put in there to make that thing be 0. Because you're going to square it, it's going to be positive, you're going to add 1. Make it 0. Other questions? Yeah?
Why is the h of x
None?
for the roots?
Okay, so what root did you have?
I think I had
1. So does it make it 0? Go back to the definition of a root. Does it make that fraction 0 if you put 1 in? What we're trying to say is x squared plus 1, we need it to be 0. So we're trying to square a number and get what? Negative 1. In the real numbers, that's impossible. So yes, there's in complex numbers, that's okay. But in the real number system, there's no x value that you square and get negative 1. So there's no roots. Other questions on these? Yeah?
Could you explain
I want to graph one. I'm not done. Good.
for the end results?
Yeah.
Goes y equals 1.
This?
Yeah.
Because the effective leading term is 1. No matter what x is, the effective leading term is the number 1. So as x gets very, very big, it's going to get close to 1. X gets very, very big negative, it's going to get close to 1. Same with 3. Now, here, that depends on x. So if x gets very, very large positive, then it gets very, very large positive. If x gets very, very large negative, it gets very, very large negative. Better? Let me just, if you can pack up quietly and watch, and I'll graph this one as you're packing up. So 3x squared over x minus 1, x minus 3. All right, so what are the roots? What was it again? 3x squared. X minus 3. Roots were 0. Asymptotes. 1 and 3. So undefined there. Asymptote at 1, asymptote at 3. End behavior. Approaches 3. Now that's at the end. So it can cross the asymptote in the middle of the graph, that's fine. But at the end, it's going to be 3. So way out here at the ends, when x is very, very large, positive and negative. Okay? So, and what was our end behavior? Oh, 3. Okay, so coming through here. So it's got to go through this, and it's going to have no more roots there. So it's going to look like this. Closer and closer to 3. So then it's going to, but remember, what's the multiplicity of that? 2. So what does it look like? It's going to look like a parabola there and going to head up this way. Then it's going to, there's no root there, but it has to go down to negative infinity. And then it's going to look like this. Not enough time to talk about it. Homework's due Wednesday. Yeah. I have to look at your grades. So that's it.
Oh, sorry.
Yeah.
What was it for?
Okay.
Yeah.
Yeah. You better believe it. Last time we